Welcome back. Today we're going to talk a little bit about diversity and classification. And so I can already hear the questions in your minds coming through the wavelengths to my house that are saying, why do we have to do this, Miss Oz? Why do we have to classify animals anyway? Well, it's really quite complicated to classify things, and in Miss Oz form and function, I like things to be nice and organized. And if we don't organize the 1.5 million animals that exist, it would be similar to finding something here. So you might have some place in your house that looks like this. Is it easy to find something? If so, if your parents said, oh yeah, could you go get that shirt that's in that blue box in the garage? You'd be like, oh my god, is she crazy or is he crazy? Like, why do I have to do that? So if we organize animals in a very methodical way, it's much easier to find them, whether it be in your attic or your basement or wherever it is. So organizing animals is important for a lot of different reasons. One is it makes it ease. There's a lot more ease involved in finding those animals and classifying, and there's some other reasons too, which we'll get to in a minute. So if I were to say catfish or crayfish or silverfish, I want you to think about what those particular animals might look like. And in your notes, if you could just jot those down, what you think that they would be. Maybe you want to draw it, or you could actually write it out. So just take a couple seconds to do that, and then when you're ready, come on back. So, did you guys draw this? I'd be very interested to see, and I can already hear the screams like, oh my god, this is so gross, Miss Oz, that's disgusting. I know. So the only fish, so clearly they're not all fish. The catfish is actually a fish. And the little whiskers, I guess probably that's why he got his name. The crayfish is actually a crustacean. It's not a fish at all. And the silverfish is an arthropod, and those are the ones you find in your basement when you lift up a box and they go running like crazy and you kind of freak out. They like really dark, moist environments, so they really hang out in basements or garages. Any place, probably more of a basement than a garage, but you can find them in that. They love cardboard boxes too. So if you don't have any cardboard boxes, that'll be good. So with that example, we were just talking about common names. So if I said a crayfish, that might mean something to you, but it might mean something totally different to another person. So if we were to use common names, there's a lot of room for misconception with those words, and that example that we just did highlighted that. So improving using scientific names improves communication. And again, like I said before with the garage analogy, it organizes things so it's easy to find. And if scientists are studying the same kind of organisms, no matter whether they're in Germany or Russia or France or Spain or wherever, they're all speaking the same language about that particular animal. So for your history buffs, this is a little bit of the history behind classification, and this is also in your textbook. There's not a lot of questions on this, but I do want you to kind of know a little bit about the history. So there might be one or two questions on the exam on this. So Aristotle was the first to try to put some kind of classification system in place, and because they didn't know a lot about animals, he really just I said, all right, it's either a plant or an animal, and if it's an animal, do they have blood or do they not? And then furthermore, breaking it down to say, well, where do they live? Do they live in the water? Do they live in land? And so forth and so on. Linnaeus came up with the next group, and the system that he created we're still using today, and it was based on a hierarchy that other organisms will fit into a group, and then that group will fit into another group, and so forth and so on. And then Darwin really tied things up really nicely together and showed that how organisms had been classified really provided some more proof that they shared a common ancestor, which was helping his case to show a little bit more about evolution and that connection between classification and evolution. So the Linnaean system, we use the term binomial nomenclature. Bi means two, nome is name, it's as well as nim, but binomial is two-name system. And I like to think of it as like Russian dolls. So this doll fitting into this doll, and then this doll fitting into this doll, and the largest doll contains all the dolls below it. So the largest group, if I were just to use an example, say like a kingdom contains all of the phylums. So kingdom, phylum, class. So class is found within a phylum, and a phylum contains many classes. So that's kind of how you would go about that. And if you can remember the phylogenetic tree that I have outside of my door in the hallway, the base of the tree would actually be the biggest part here, the kingdom, Animalia, and then the phylum that follows it would be Chordata. So the phylum is Chordata, and then it keeps branching and branching and branching out. But all of the species file into the next group of genus and so forth and so on. So you can always kind of refer to that picture or that thing outside the hall, the phylogenetic tree, or you can think of it from a Russian doll standpoint. So you might have noticed on the tree outside of the door is that there are some animals that are listed, and not only do I have the kingdom Animalia, phylum Chordata, everything listed, but then the students have also put their animals at the end of those pictures. So if you haven't checked it out, you could kind of look at that. It's kind of a nice little visual. So going from the largest to the smallest, we have a mnemonic device that will help us remember this. So it's Dear King Philip came over for good spaghetti. Great mnemonic to have, just like fame, just like both, just like my guppy flow. Any one of those mnemonics is really a very important thing, not only for your exam, but for the final as well. So just to review, that domain is the largest group, kingdom follows behind that, and a bunch of phylums are contained within the kingdom, like the Russian dolls. And if you were to write your species of, say you were researching an animal, and actually you need to do that for your speciation project, you need to write what you think your animal's name would be. So how do you go about that? So some of the rules are, the first time that you use that name in your, say, project and you're writing it out, let's just pretend that this was your rodent. So Panthera pardus. So the scientific name consists of two words, the binomial nomenclature. The first word is the genus and the second word is the species. The genus is always capitalized, the species is lowercase, and if you were typing this out, it would be in italics, and that's an important piece. If you were handwriting it, instead of italics, it's difficult to write in italics, you would just underline the whole thing. So that would be almost like a non-verbal to the person reading it, that this should be italicized, but that you're handwriting it and that you really can't do that. The next time you want to talk about your species that you've already named, it's appropriate to take that genus and shorten it. So it's just one letter and it's capitalized with a period, and then you put lowercase the species. Okay, so again, when you're doing this for your speciation project, you want to list it entirely genus and species the first time you use it, and then it's appropriate to shorten it up after that. So classification, I really love this slide because it really highlights the connection between the evolutionary history or the ancestry, their common ancestry, and the link between that common ancestry and how we classify animals. So it's important to kind of think about that, and that everything we did in chapters before, like 14 and 15, feed into how we actually classify. So the organism's evolutionary history is important. So evolutionary history, from a purely definition standpoint, is the term is called phylogeny. And if we use our prefixes here, gen, anybody remember? It's good, it's origin of. Philo with one L is good, it's tribe or clan. So it's the origin of your tribe or clan. So think of it as your family tree, the origin of your tribe or clan. So if we were to recreate someone's family tree like this, that's really showing us your evolutionary history, and we would do the same for animals. So if I was going to try to recreate a phylogenetic tree, what information do you think that we would need? And so what I'd love you to do right now is just pause for a moment, think about the things that a scientist would need in order to recreate a phylogenetic tree. So just pause it for a moment and then come right back. Alright, how'd you do? Well, hopefully you thought, okay, this is evidence. I'm hoping that that's the case. So if you were thinking Well, the evidence to evolution is fossils, anatomy, metabolic or molecular, and embryologic. You were on the right path. Okay, so anything that we would use to prove evolution is also going to help us with classification. Remember, classification goes hand in hand with evolution. The big ticket items that we use in order to do this is specifically their anatomy and molecular. So we would compare, say, cytochrome C, hemoglobin, just like we did the simulation. We'd also look at bones, and potentially some microscopic anatomy as well. But it's really important to kind of remember from chapters previously that it can be confusing, because if we have analogous structures, remember those look the same on the outside, but if we were to kind of tear away the outside structures like the skin and feathers and so forth and so on, once we get into the inside, their bone structures are very different. So although they might look similar and function similarly, the bone structures on the inside are different, and if they are, that does not prove common ancestry. And the reason why that would be is some environmental factor that created those that made those organisms successful if they had that particular structure. So we say that that's due to convergent evolution. And a great example that's in your textbook are wings. So I know that you've seen these before, but these are analogous structures that are anatomical pieces of information, but it does not show common ancestry, so we would never put these together on the same phylogenetic tree. This is one example of a phylogenetic tree that's been created, and here they're looking at structures, and here we can see all of these structures that are listed here. So a hagfish does not have a jaw, but a perch does, where a salamander has lungs and a perch does not. So what could we say about a pigeon? So does a pigeon have fur and mammary glands? What do you think? They do not. Only thing that has fur and mammary glands are the chimp and the mouse. So as you go up in this phylogenetic tree, you're going to see that as organisms develop those structures, they are above where they actually put this. So that's how you would actually read that. And so we can create a phylogenetic tree that really highlights those structures and how they're related. You can actually create a phylogenetic tree yourself by using a dichotomous key. A dichotomous key is a fancy term that's used, and you probably have seen or heard about this before, maybe in middle school. It helps you to identify organisms. It also can help people that have an unknown organism. You're trying to figure out where they actually fit in. So usually you ask a certain question, well, do they have jaws? Yes or no? And based if they have jaws, you go yes, then you go up the phylogenetic tree, and then you kind of know where to place them. It's kind of like a good game of 20 questions. I like to think of it that way. So if we were to make a dichotomous key on this, we would say, does it have jaws? Yes or no? Then you say yes, and then you say, well, does it have lungs? If it doesn't have lungs, well, you know you've got a perch. So that's kind of how that would go. And in class, we'll actually work out how to create these. And we'll be doing that in the near future. It's not going to be next class, but I wanted you to have exposure on how that is actually done. So kind of remember that a dichotomous key is like a good game of 20 questions, and then that will help you be prepared for when we do that later in the week. So I hope that was helpful, and I will see you guys next class.